8.2 polar graphs. So 8.2, we're going to be talking about how to graph these different things from the polar form, how to graph polar graphs where you're not able to actually graph them on a rectangular. You could, but you just don't have the correct type of graph as far as the polar grid gives you, like the radius and theta. So we're going to look at those. Some things that you should know first is how to change your calculator. So if you're going to use your calculator, which you should, use your calculator, you have to change the mode. So you have to go into mode and change it to polar and then go to polar GC. And then your angle should be in radians. This is the format for the TI-89. In the graph screen under F1 tools, number 9, coordinates, make sure you go to coordinates and then you'll select polar. For the 84 and the 83 format, second zoom, select polar GC. So make sure you guys find that. You do have to change the format. And then your window range. So you're going to see this, your theta min, theta max, your x min, x max, y min, x or y max, and then your theta step, x scale, and your y scale. So make sure you can use these. For theta, notice that it says you could use maybe smaller for some graphs. You may need to change the theta, x, and y min max for some graphs. So you'll have to think about how big is your x, how big is your y, and then go from there. But this is a good place to start to show your graphs. Then you can also use zoom, zoom fit, zoom square to make your graphs proportion correctly. So you do have to deal with the calculator first. Okay, so here is one of them. You're basically going to see all the graphs. I'll show you them, then I'll graph them for you. But this is theta equals 3 pi over 4. And so if you think about it, 3 pi over 4, if you think about it, is 1, 2, 3 pi over 4. And normally what we do is we go from the origin and we draw that to 3 pi over 4. But I need to remind you guys and tell you that once you have this side, you should actually extend it, all right, at 3 pi over 4. That line is extended. In past years, students only would graph this portion of the graph and they'd lose half credit. But you actually should graph all of it. Theta equals 3 pi over 4 is a straight line at 3 pi over 4 and extended. All right. Here are circles. So some things that you should know. We'll look at these equations. That when the radius equals a number, it's a perfect circle centered with the center at the origin. All right, with a radius of whatever you determine A is. Now, if you have a circle that's like this, with this equation, R equals A sine of theta. Well, in that case, notice that this is the sine and your circle is on the y-axis. All right, now you can think about it. If A is going to be negative, it'll be below. Right now, we have it positive, so it's above. And then the last one, R equals A cosine theta, it's on the x-axis. It's on the x-axis. X is your cosine and y is your sine. And your circle's on the y-axis and your cosine is the circle's on the x-axis. All right, same thing. If A were negative, it'd be flipped over on the negative x-axis. Okay, so let's move on. Sorry if some things didn't transfer really, really well to get you these videos. Okay, so equation forms for some polar graphs. So, like I said, I already went ahead and I shared the solutions to you. I'll just talk you through them. So this would be a good place to, after I talk about it, pause, get you some notes down. But for circles, if R equals just a number, it's centered about the origin, just like this one. So this first one, it's R equals 4. Well, the radius is in 4, so 4 in every direction centered on the origin. So if R equals just a number, that's the first one here, equals just a number, the circle is centered about the origin. Now, here's the next one. If R equals A cosine theta, all right, remember it's on the x-axis. A is your diameter. That's important that you understand that A is now your diameter, where positive A cosine, this is what I talked about before, is on the positive x-axis, and negative A cosine is on the negative x-axis. All right, let's go down below. So here's this first one, the second one, R equals 4 cosine theta. Remember that 4 is your diameter. All right, that gets mixed up sometimes as the radius, but it is your diameter. So it's on the positive x-axis, all right, positive x-axis, because the 4 is positive, and it's cosine, so it's on the x-axis. So from the origin, I go out 4. 1, 2, 3, 4. and then I make a perfect circle from there. For the sine, the third one up here, r equals a sine theta. Similarly to the cosine, a is the diameter. We're now a sine of theta. A sine of theta is on the positive y-axis, where a sine of theta, or negative a sine of theta, is on the negative y-axis. So looking at the third example, r equals now negative 6 sine of theta. All right, sine is going to be on the y-axis. The negative tells you it's going to be on the negative y-axis. So let's count. 1, 2, 3, 4, 5, 6, and then you make a perfect circle. Be a chance for you to pause right here and go ahead and write down some important notes. Okay, let's talk about the cardioids. Our cardioids, there's 3 different kinds. One's called a limacone, and don't mess with me about the pronunciation of all these, but that's how I say it. Limacone with an inner loop. We're going to talk about A and B, that when A is less than B, this is important. When A is less than B, it's a limacone with an inner loop. All right, passes through the origin, but it has an inner loop, kind of like it folds back in on itself. A is less than B, folds back in on itself. That's how I remembered it. A cardioid, all right, A equals B. So when they're the same, it's a cardioid. All right, and it looks like this. That's a regular cardioid. I've always said it looks like kind of like a heart, upside down heart, but everybody messes with me that it doesn't, but whatever. Cardioid, cardiac arrest, whatever. That's just how I remembered it. And then A is greater than B. It's dimpled. It's a dimpled limacone. So now A is greater. So now it goes around the origin. So when A is greater than B, it does not fold back onto itself like the limacone did, but a dimpled limacone, it goes around the origin because A is greater than B. All right, so there's just different ways. Good chance for you to write down some notes. Okay, let's look at the examples of the cardioids. Okay, so now the first thing is if r equals a plus or minus a cosine of theta, your y-intercepts, this is very important that you understand this, your y-intercepts at positive and negative a. All right, so I'm going to take that part right there first. This is just this first part. I'm going to show you on the first example. All right, so it's cosine, so it's going to be on our x-axis. Your y-intercepts are at positive and negative a. All right, so in this first example, a is 3. And notice they're the same. A and B, as in the previous slide, we said if A was equal to B, in this case, you have A and A, so we're calling them the same, 3 and 3. Well, your y-intercepts are positive A and negative A. So I go 1, 2, 3, and 1, 2, 3, and I plotted both of those points. Okay. The next thing says origin to the x-intercept is equal to A plus A. So A plus A would be 3 plus 3, which equals 6. And so what is that? So that is origin to x-intercept is equal to A plus A. So from the origin to the x-intercept, I go 1, 2, 3, 4, 5, 6. So there's my next point. All right. And then again, if A is cosine theta, it's to the right. And if A is a negative, it's to the left. So if this were a negative A right here in the middle, instead of being a plus, instead of going this way, I would have gone that way. All right. And then from there, we can make the graph. Now I'll click here and you're going to see both answers. But looking at the first example, there's our cardioid. Looks like a heart, cardiac arrest. All right. Does not fold back on itself, does not go around the origin. Second example, it's a sine. All right. Remember that A equals A, so it's a cardioid, and it's 4. So that's now on the x-axis. So the second one up here, x-intercepts are positive and negative A. So A is 4, left 1, 2, 3, 4, and right 1, 2, 3, 4. And then the origin to the y-intercept, again, is A plus A. In this case, it would be 4 plus 4 equals 8. And so your y-intercept, and it's negative, so instead of going up here, instead of going up there, we're going to go down. All right, and so if I count 8, and I know the numbering is just a little bit off, but the point's a little bit off just because of the transferring of it. But if I count down 8 from the origin, 1, 2, 3, 4, 5, 6, 7, 8, there's that point. All right, and now I can make my cardioid. You have to know what the cardioid looks like. Looks like a heart, and there it is there. Okay, let's move on. Limacone with a dimple. Now this is where A is A is greater than B. All right, so it goes around the origin. Take a look at all the information up here. The first one is cosine. We know that's going to be on the x-axis. A greater than B. You can look at the first example. Actually, it's over here where A is greater than B. 6 is bigger than 4. And then the y-intercept is at positive and negative A. This is important. So the y-intercepts are at positive and negative A. So we go down to the cosine. We're talking about the y-intercepts. A is actually 6. So if I actually write that down, A to be 6. Oops. A equals 6. B is actually 4. So your y-intercepts are at positive and negative A. So let's just take a look at that. So I go up for the y-intercepts, 1, 2, 3, 4, 5, 6, and I go down 1, 2, 3, 4, 5, 6. All right. And then it says origin to the near x-intercept. So you should know that there's a near and there's a far. So a near and a far. All right. The near and far. So let me just show you the limacone with a dimple again. The example here. Limacone with a dimple in it is like this one. Here's the near side. Here's the far side. All right. Near, far. Obviously, you can see one's bigger than the other. Let's go back to it. All right. And so it says to the near x-intercept, it's A minus B. So we would talk about 6 minus 4. Oops, 6 minus 4 equals 2. All right. And so if I go the near side, 2, and by the way, it's a negative, so that means it's supposed to be the biggest part is supposed to be on the negative x-axis. So that means that the smaller side should be on the positive side. So if I count 1, 2, that's where that point comes from. And then to the far x-intercept, it's A plus B. So 6 plus 4. 6 plus 4 equals 10. And so now I count to the far side, should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 off the graph. All right. Take a look at that answer, and there it is. A limacone with a dimple where A is greater than B. A is greater than B. And you can see how it goes around the origin. I want you to take a look at the first example for the sine. Look at the information for it. Everything's pretty much the same. It's just on the y-axis. It's also positive, so it's on the major sides on the positive y-axis side, smaller sides on the negative side. And then I count out A being 4, so I count out 4 in every direction, that kind of thing. All right, and then take a look at the graph. Make sure you do that example. All right, make sure you understand. Take a look at the information. If you have to pause, but get it down. Moving on to the loop. All right, the loop, I always said folds back onto itself. All right, how do I know it folds back onto itself? A is less than B. Oh no, it's less than B, so it must fold back onto itself. That's just the way I remember. If A were greater than B, it goes around the origin. All right, it's bigger. It goes around the origin. But if A is less than B, it needs to fold back in on itself. Some of the information is kind of the same. All right, when it's the cosine, where R is equal to A plus or minus B cosine theta, the y-intercepts at A are at plus or minus A. So take a look at this first example. And this should say cosine for this right here. Try to fix it a little bit, but it should say cosine. I'll actually even rewrite it for you. It should say cosine. Should be A plus B cosine of theta is the form of it. But anyway, if the y-intercepts are at plus or minus A, all right, that's fine. That's the cosine. Your y-intercepts plus or minus A. A in this case is 3, so I count up 1, 2, 3, and down 1, 2, 3. And then here's some tricky parts. The near x-intercept, remember it folds on top of itself, and a far x-intercept. That's where it reaches way farther out. So let's go look at the loop again. Here it is here. This is the near, and this entire distance is the far. All right. Keep it in mind that you have to recognize that A is less than B, so it should fold back on top of itself. All right. So here it is. All right. So if that's the case, the near one is A minus B. All right. So 3 minus 5. 3 minus 5, and watch what kind of happens. 3 minus 5 is equal to -2. And if you think about that, oh, you're saying, okay, that should fold back onto itself. It's negative. All right. I don't care if you think of it as 2 or -2. You should recognize that it does. It should, the bigger side should be on the positive y or positive x axis because it's positive here. And so now I count out 2, 1, 2 folding back on top of itself. And then the far part is a plus b, kind of like how it was before. So 3 plus 5 equals 8. So the far side, I count out 8. So I go 1, 2, 3, 4, 5, 6, 7, 8. All right. Now I have all my points. All right. Again, they're just telling you if A is positive, it's to the right. If A is negative, it's to the left. Take a look at what the graph looks like. There you go. All right. Keep in mind, I know what students used to mess this up, how they used to mess this up. They would forget to go through the origin. It still goes to the origin. All right, so you have all those points. The way you'd actually make it, I'll actually try to make this previous one for you. Let's see. Oh, sorry. Here we go. All right. So it actually goes like this. There's no perfect way of doing this. All right. So you can see how I have my loop here. Okay. Let me start that over. Let me start that over. All right. So here we go. So I'm going to make the loop. When I make that loop, it comes from this way. There's the loop. Then it comes back down all the way out here. There you go. Applause necessary right there. All right. That's actually pretty good using just a stylus. Same thing for the sign. Notice it's negative. There's some things you can notice as you try to look at this one. It's on the negative y-axis. Your a plus, your positive and negative a is on the x-intercept. A is here is 2, so left 2, right 2. And then a minus b. A minus b would be 2 minus 4, which would be -2. That negative just tells you what side it would be. -2, so 1, 2. And then a plus b would be 2 plus 4. 2 plus 4 would be 1, 2, 3, 4, 5, 6. Make the graph. Here's all the work for it. There you go. 2 minus 4 is -2. 2 plus 4 is 6. So the negative y-axis. Okay. Okay, here's a little summary. This is where you should pause at some point and actually write this down. What a cardioid is, it's where A equals B, but technically B is just A, so A equals A. Limacone with a dimple around the origin, A is greater than B. Limacone with a loop, A is less than B. All right, so it loops back onto itself. All right. Last couple things are lemniscate or lemniscate. Couple things about that. All you have to recognize is that, and I'm going to keep this simple for you guys, is that recognize for the sign, lemniscate loops on the pi over 4 rotation line. All right. R squared equals A squared sine 2 theta. That will be the form of a lemniscate. So just this right here. Looks complicated, but it just gives you the loop. I call it a lemniscate or a lemony biscuit. All right. That's how I used to remember it. But if it's the cosine, then it's lemniscate loops on the horizontal axis or on the x-axis. Remember, the cosine is your x. It's on the x-axis. All right. The sine is a little bit different. It's on the it's not on the y-axis, not straight up and down, but it's on the pi over 4 rotation line. All right. Here's a couple examples. Use table values to locate theta. That corresponds to petal length. Loops are length square root of a. That is important. All right, so square root of a. So if you look at the first example, r squared equals a squared sine 2 theta. Well, a squared is 9. So we'd actually take the square root of 9 to figure out if that's 3. You also have to recognize that it's the sine. So I count out 1, 2, 3. So I count out 1, 2, 3, and 1, 2, 3 on pi equals 4, on the pi equals 4 rotation line. On this example over here, it's on the x-axis, it's a square root of 16. You just have to be careful that you recognize it's the square root of 16, which is equal to 4. And so on the x-axis, I go out 1, 2, 3, 4, and 1, 2, 3, 4, and then I make my loops. All right, so if I make my loops, there they are. All right, they don't have to be perfect, and I actually made them kind of a little bit different, the green and the blue. Doing the best you can. Make sure they look somewhat nice and that kind of thing. Make sure you have the forms of all the equations down and the names of them, and then the diagrams of what they look like in your notes. So when you take your test, you recognize what the graph should look like. Lemniscate, and then these rules right here about the cardioid, limacone with the dimple, and a limacone with the loop. If you have any questions, let me or Ms. Zara know, Mr. Hall or Ms. Zara know, and we shall be able to help you out.